You look up at the sky on a clear day, and the sun just seems like this, big, reliable yellow circle.
Right, like a celestial light bulb.
Exactly. A light bulb that clicks on in the morning, clicks up at night, and never really changes.
Yeah.
Unchanging, perfectly calm, just, doing its job. But crack open the actual astrophysics, and that peaceful image shatters
Oh,
instantly.
shatters completely.
Yeah, you realize you are looking at this chaotic, violently active nuclear engine that is basically holding itself together by a thread.
Which is wild.
Mm.
So to absolutely crush your New York Regents exam, we're kicking off a 20-part deep dive series to get you there. And today is all about nuclear fusion and the sun's energy.
Our mission here is to take these massive, heavy science concepts from your review sheet and turn them into a vivid working picture of how our solar system's engine actually operates.
Because when you can picture the physical mechanics behind the vocabulary, the science becomes entirely intuitive. Exactly. The sun is not just a glowing ball in the sky. It is a massive, complex structure fighting a constant battle against its own weight.
Okay, let's unpack this.
Yeah.
Because before we even get to, like, the sunlight warming our faces, we have to figure out how the sun manages to exist at all. I mean, it is essentially a giant ball of gas.
Right, mostly hydrogen and helium.
Right, but gas naturally wants to expand and just drift away,
Hmm.
especially in the giant vacuum of space.
It does.
So something has to be holding it together, and that thing is gravity.
And not just a little gravity. I mean, the sun contains about 99.8% of all the mass in our entire solar system.
Hey, 99.8%.
Yeah, almost everything. You
Yeah.
could fit over 1 million Earths inside of it. So because its mass is so unimaginably huge, the gravitational pull is just terrifyingly strong. It is constantly pulling all of that gas inward, basically trying to crush the entire star down into a tiny, dense point.
But the sun hasn't crushed itself into a tiny point. It's, maintaining its massive size. So there has to be an equal force fighting back against that inward crush of gravity. Think about holding a giant, heavily inflated balloon.
Okay.
You wrap your arms around it and squeeze inward as hard as you can. Your arms are gravity, right? Trying to crush the balloon. But the balloon doesn't collapse because the air pressure inside is pushing back out against your arms.
That is a perfect analogy. And in the sun, that outward push, the air in the balloon, is the energy created by nuclear fusion. It is a delicate, continuous tug of war. Gravity pulls inward, and the outward pressure from nuclear fusion pushes back.
And there's a specific vocabulary word for that balance, right?
Yes. The balance between those two opposing forces is called hydrostatic equilibrium, and it is literally the only thing keeping the sun stable. If that balance wavers, the entire structure of the star changes.
Which makes you wonder, what happens if they aren't perfectly matched? If gravity pulls a little too hard or fusion pushes a little too much, does the whole thing just, fall apart?
Well, the sun actually functions like a brilliant, self-correcting thermostat.
Oh, really? How does that work?
So let's say the outward pressure from nuclear fusion slightly decreases. Suddenly, gravity has the upper hand. Because gravity is stronger, it pulls the gas inward, causing the sun to contract.
Makes sense.
But when you compress a gas, you increase its density, its pressure, and its temperature. So as the sun's core is squeezed by gravity, the temperature and pressure skyrocket.
Oh, I see where this is going.
Right. That extreme heat and pressure crank the nuclear fusion process right back up. The outward push gets stronger, forcing the sun to expand back to its normal size, perfectly restoring the balance.
Wow. So if the fusion engine goes into overdrive and creates too much outward pressure, it pushes against gravity and makes the sun expand. But because the gas is expanding, it cools down.
Exactly.
And the cooler temperature slows the nuclear fusion back to a normal rate, and then gravity pulls it back into place. It's this constant sort of breathing adjustment.
It really is. It's a millions of years long dance. But, and this is key, that balance is only maintained as long as the sun has nuclear fuel to burn. When that fuel eventually runs out, the outward push will stop.
And gravity wins.
Gravity will win the final round of the tug of war, and the star will collapse.
Okay, so to really understand this engine, we have to figure out what this fuel actually is. We know nuclear fusion is the outward push keeping the sun alive, but we need to zoom right into the center of the star to see, the mechanics of how that push is manufactured.
Deep inside the sun's core, the environment is just extreme. It is the only place in the entire star where the inward crushing force of gravity creates enough pressure and high temperatures to actually force atoms together.
How high are we talking?
We are talking about 27 million degrees Fahrenheit.
That is just incomprehensible.
It really is. But that is the threshold required for nuclear fusion.
And the main ingredient, the fuel sitting in that core, is hydrogen, right? The intense pressure and heat take these hydrogen atoms and force them to combine or fuse into helium atoms. But wait, atoms usually repel each other, don't they? They don't want to be mashed together.
They absolutely repel each other. Hydrogen nuclei are positively charged protons, and just like trying to push the two positive ends of a magnet together, they fiercely resist.
Right, they just slide away from each other.
Exactly. The only way to overcome that magnetic repulsion is to get them moving at blistering speeds and crush them together so hard they have no choice but to bind. That is why the core's extreme temperature and pressure are non-negotiable for fusion.
I like to visualize this using modeling clay.
Oh, that's a good one.
Yeah, imagine you have two separate equal pieces of clay. Those are your hydrogen atoms. You weigh them on a very precise scale.
Yeah.
Then, using immense force, you smash those two pieces of clay together to make one single larger piece of clay.
Man, that new piece is your helium atom.
Exactly. Now, you would expect that new helium piece to weigh exactly the same as the two smaller hydrogen pieces combined. But in the extreme magic of the sun's core, the new helium atom weighs slightly less than the original hydrogen atoms did. There is a tiny bit of missing clay.
What's fascinating here is what happens to that missing mass. It doesn't just vanish into nowhere. The universe doesn't allow matter to simply disappear. It transforms.
It turns into something else.
Yes. This is the exact mechanism Albert Einstein described with his famous equation E equals mc squared.
The equation everyone knows, but rarely stops to actually break down.
Right, so let's break it down because it is the secret to the entire solar system. In E equals mc squared, the E stands for energy and the m stands for mass. Specifically, that tiny bit of missing mass from our hydrogen to helium fusion.
Okay, mass and energy. Got it. And the C.
The c represents the speed of light. Now, the speed of light is about 300,000 kilometers per second. It is a massive number, but the equation says we have to square it. So you multiply 300,000 by 300,000.
You get a ridiculously huge number.
Yeah, an astronomically huge multiplier. What the equation reveals is that mass and energy are the same thing, just in different forms. When you take that tiny microscopic bit of missing mass from the hydrogen atoms and multiply it by the speed of light squared, you get an explosive, monstrous amount of pure energy.
Wow. So the sun isn't burning like a giant campfire.
No, not at that.
Because a campfire is a chemical reaction,
Right.
like wood combining with oxygen.
Yeah.
The sun is doing something fundamentally different. It is literally destroying a tiny bit of physical matter and converting it directly into high-energy output.
It is annihilating matter to create light and heat. 4 million tons of physical mass are converted into pure energy every single second in the sun's core.
Every single second.
Every second. That violent continuous explosion is the outward push fighting gravity.
Okay, here's where it gets really interesting. Because the core just manufactured all this intense energy. It smashed the hydrogen, made the helium, lost a little mass, and created this blinding flash of energy. But that energy is trapped deep in the center of the sun. And we live 93 million miles away on Earth. So how does that energy actually get out of the sun to warm our planet?
Well, the energy produced by nuclear fusion starts off as high-energy photons. You can think of photons as tiny packets of light in energy.
Okay, tiny packets of light.
Right. These photons are born in the core, and their only goal is to travel outward through the layers of the sun, escape the surface, and travel through space via electromagnetic waves. The vocabulary term for this transfer of energy through space is radiation.
Radiation. But if these photons are essentially light, and light is the fastest thing in the universe, it should just zip right out of the sun, right?
You would think so.
I mean, it takes sunlight about 8 minutes to travel the 93 million miles from the sun's surface to Earth. Yet the physics show it takes hundreds of thousands, sometimes millions of years, for a photon just to travel from the core of the sun to its own surface. Why is the fastest thing in the universe taking millions of years to make a relatively short trip?
Because the interior of the sun is not empty space, the layers surrounding the core are unimaginably dense plasma. A photon of energy cannot travel in a straight line.
It bumps into things.
Exactly. The moment it moves a fraction of a millimeter, it crashes into a gas atom. That atom absorbs the photon, holds it for a split second, and then fires a new photon out in a completely random direction.
It's like trying to sprint at top speed across a massive sports stadium that is packed shoulder to shoulder with millions of people.
Yes. You can't just run straight across the field.
Right, you take one step, crash into someone, and bounce sideways. Then you crash into someone else and get shoved backward. You are moving fast, but you are zigzagging so erratically that it takes you hours just to move 10 feet.
Astronomers call this process the random walk. The photon gets absorbed and re-emitted billions and billions of times, ricocheting through a ridiculously crowded space.
Wow.
Because its path is entirely random, bouncing up, down, left, right, and backward, it takes a single packet of energy up to 1,000,000 years to finally bump its way to the outer edge of the sun.
And only when it finally hits the surface and breaks free into the empty vacuum of space does it hit the gas pedal, traveling as radiation and zooming to Earth in just 8 minutes.
Exactly.
Which means the sunlight that is hitting your skin right now, providing heat and light to our planet today, was actually created in the core of the sun before modern humans even existed.
We are constantly bathed in ancient energy.
That is mind-blowing. But because that photon took millions of years to escape, we're essentially looking at the sun's deep past. If the internal processes are that delayed, and the whole tug-of-war balance between gravity and fusion plays out over billions of years, we can't possibly sit around and wait to see how our sun will evolve.
Right, we won't be around when the hydrogen fuel runs out.
So how do scientists actually know what will happen to our sun in the future?
This is a classic problem in astrophysics. You cannot observe stellar evolution in real time. To understand the full lifespan of our sun, astronomers are forced to look elsewhere. They observe other stars in the galaxy.
Oh, I see. It's like if an alien visited Earth and wanted to understand the entire life cycle of a human, they wouldn't pick one newborn baby and sit there watching it for 80 years. That takes way too much time.
Definitely.
Instead, they would just walk through a busy shopping mall. They would see newborn babies, teenagers, middle-aged adults, and elderly people all at exactly the same time.
Right.
And by observing different humans at different stages of life, the alien could instantly piece together the human aging process.
That is a brilliant way to put it. If we connect this to the bigger picture, the Milky Way galaxy is our shopping mall.
I love that.
By observing the properties of billions of other stars at different stages of their lives, astronomers map out a clear blueprint of how stars are born, how their internal engines change, and how they eventually die.
But when they are scanning this galactic mall, what exactly are they measuring? They can't exactly put a thermometer inside a star light years away.
No, they can't. So they rely on two critical observable metrics: luminosity and surface temperature.
Okay, luminosity and surface temperature.
Yes. Luminosity is the true intrinsic brightness of a star. It's the total amount of energy it is actually radiating out into space.
Got it. And surface temperature?
Surface temperature tells us how hot the outer layers are, which also dictates the star's color. Hotter stars burn blue, while cooler stars burn red.
Okay, so by charting those two things, how much energy the star is pumping out and what color its surface is burning, they can figure out exactly what stage of the tug-of-war those stars are in.
Precisely. They can look at a highly luminous, massive blue star and know its core is burning through fuel at a terrifying rate. They can look at a giant, cool red star and know it has run out of hydrogen in its core and is now expanding outward.
Oh, wow.
By reading these stellar blueprints across the universe, we know our own sun is a middle-aged, average yellow star with enough hydrogen fuel to keep its current balance for about another 5 billion years.
Okay, 5 billion years of stable hydrogen fusion. But does that mean the sun is just a perfectly steady, constant light bulb day to day?
Not at all.
I mean, we've looked at the massive billions of years timeline, but what happens on a Tuesday? Does the sun change?
The sun's radiation output is absolutely not constant. It varies significantly over time. The sun has its own highly turbulent weather system, driven by its complex magnetic fields.
Magnetic fields. See, I always think of the Earth having a magnetic field with the North and South Pole. Is the sun's field similar to ours?
It starts out similar, but there is a major difference. The Earth is a solid rock, so it all rotates at the same speed.
Right.
The sun is a giant ball of plasma and gas. Because it isn't solid, the gas at its equator spins much faster than the gas near its poles.
Wait, different parts of the sun are spinning at different speeds?
Yes, this differential rotation takes the sun's magnetic field lines and twists them, tangling them up tightly around the star over time.
So what does this all mean for us? If the magnetic field gets tangled up like a twisted rubber band, Eventually,
Mhm.
that rubber band is going to snap under the tension. Right.
And when it snaps, you get a solar flare. A solar flare is a sudden, violent eruption of charged particles and intense electromagnetic radiation from the sun's surface. It's caused by the release of that twisted magnetic energy.
When I hear flare, I picture a literal volcano erupting fire on the sun's surface. Is it physical matter shooting out, or is it pure energy?
It is a massive blast of radiation across the entire electromagnetic spectrum, accompanied by a wave of high-energy charged plasma. And these eruptions don't just stay near the sun, they blast out into the solar system,
So if Earth happens to be in the crosshairs of that blast, those charged particles slam into our planet's magnetic field.
which impacts our space weather. It creates stunning geomagnetic storms, which we see as the northern and southern lights.
Which are beautiful.
They are. But the consequences aren't always just pretty colors in the sky. A severe solar flare can dump so much energy into our atmosphere that it disrupts radio communications, blinds GPS satellites, and induces strong electrical currents in the ground that can literally blow out power grid transformers on Earth.
The sun is highly active, and it can actively mess with our modern technology. That is intense. But these flares seem sudden and random. Are there any variations that we can actually predict?
Yes. As those magnetic fields twist and tangle, they create cooler, darker patches on the sun's surface called sunspots.
Sunspots.
Right. The intense magnetic knots prevent some of the heat from the core from reaching the surface in those specific areas. And what scientists have observed is that the number of sunspots follows a very predictable 11-year cycle.
The sunspot cycle. So the sun goes through a period of being highly active, heavily spotted, and prone to solar flares, and then 11 years later, the magnetic field resets, the spots disappear, and it quiets down.
Exactly. It ramps up and calms down like clockwork.
Yeah.
But beyond that 11-year cycle, the sun's overall radiation output can also vary over much longer time frames. We are talking centuries or millennia.
Okay.
These non-cyclic changes in its internal processes are slight, but even a tiny fraction of a percent change in the total radiation reaching Earth over a few hundred years can play a significant role in historical climate shifts. The sun's mood swings directly dictate the environment of our entire solar system.
It totally transforms how you see the sky. I mean, it isn't a static painting up there. It is a massive nuclear engine balancing on a razor's edge of gravity and fusion pressure. It is literally destroying mass to create energy through E equals mc squared, forcing photons through a million-year random walk just to reach the surface, and constantly twisting its magnetic fields into sunspots and flares that can knock out our power grids.
And every single one of those concepts, gravity, fusion, radiation, luminosity, the sunspot cycle, they're all interconnected parts of a single machine. When you understand the engine, the vocabulary naturally falls into place.
You've got the mechanics down? Let's do a rapid-fire recap to lock it in for your Regents prep. We started with the ultimate tug of war. Gravity continuously pulling the sun's massive weight inward, perfectly countered by the outward pressure of nuclear fusion pushing back.
Then we zoomed into the intensely pressurized core, where hydrogen atoms are smashed together to form helium. This process leaves behind a tiny amount of missing mass, which is multiplied by the speed of light squared to release an explosive amount of energy.
We track that energy as high-energy photons, surviving a brutal millions of years long random walk through dense plasma just to reach the surface, where they finally travel to Earth via electromagnetic waves known as radiation.
We explored how astronomers study the luminosity and surface temperature of other stars in our galactic shopping mall to predict the billion-year lifespan of our own sun.
And finally, we uncovered the sun's turbulent space weather, driven by twisting magnetic fields that create sudden solar flares, 11-year sunspot cycles, and long-term variations that impact Earth's climate and technology.
It is an incredibly dynamic system operating on touch scales that are almost impossible for the human brain to fully grasp.
Speaking of timescales, as you pack up your notes, I want you to think about that traffic jam of radiation. If the sunlight hitting the ground outside your window right now was actually forged in the immense crushing heat of the sun's core millions of years ago, what kind of energy is being created in the core right this exact second?
This raises an important question. The Earth is experiencing the sun's ancient history. What incredibly powerful forces, what violent atomic collisions are happening right now, trapped deep inside the sun, that humanity won't even feel for another million years.
That is something to chew on. Keep up the great studying. You've got these physics concepts locked in. Take a break, grab a snack, and we will see you right back here for part 2 of our deep dive series.